Alright, so this is going to be the intro to Unit 3, Notes 1. Unit 3 is all about forming compounds with different elements. So in the past unit, we've been looking at only elements and the properties of different types of elements. This unit is going to stress mostly what's going to happen when we start mixing these elements together, forming compounds. Remember, we talked about in Unit 1 how a compound is a mixture of multiple elements. Okay, so when we combine these two elements and these elements start to bind to each other, that's when we start seeing compounds. So what I'm going to do is I'm going to go ahead and hide here, and then we can go ahead and continue with the material. So just continuing on, once again, we're focusing only on compounds. Specifically in this section of notes, we're going to take a look at ionic compounds. All right, what we want to address first is why are chemical names and formulas very important in chemistry? Okay, well, one key reason is because there was an example of a study where people were trying to ban this substance called dihydrogen monoxide. They've even set up a website where I'll show you the website right here. It's a website showing us the different bad effects of this compound called dihydrogen monoxide. So if we take a look at some of the bad effects of dihydrogen monoxide, what are some of the dangers associated? Death due to accidental inhalation. Prolonged exposure to solid DHMO causes severe tissue damage. Excessive ingestion produces a number of unpleasant, though not typically life-threatening side effects. DHMO is a major component of acid rain. Gaseous DHMO can cause severe burns, contributions to soil erosion, so on and so forth. There's a huge list of reasons why this compound, dihydrogen monoxide, can be very bad for human beings. All right, so why do we want to be careful with the chemical names? Well, the formula for dihydrogen monoxide is H2O. And you might already know what H2O is. And in case you don't know, H2O is just water. All right, so that's the accepted chemical name or IUPAC name for water. IUPAC is just basically when you see that, that's going to be like the standard for naming compounds. Again, the formula is H2O, that's water. And the systematic names can include all sorts of different types of names for the compound. We have dihydrogen monoxide, dihydrogen oxide, hydroxyl acid, hydrogen hydroxide. All of these are appropriate names for water, but we just simply call it water. So this is why it's very important for us to understand chemical names, because if we take a look at this list of the dangers of dihydrogen monoxide of water, are they all true? Well, let's take a look. Death due to accidental inhalation of DHMO, even in small quantities. Yes, if you inhale a lot of it, that means you'll probably drown, right? Even in small quantities, though, you can develop things like pneumonia. Pneumonia is basically where you get liquid in your lungs and then you get a bacterial infection, so that can be bad. Prolonged exposure to solid DHMO causes severe tissue damage. Solid DHMO is ice, so yes, being exposed to ice can have bad effects. Excessive ingestion produces a number of unpleasant, though not typically life-threatening side effects. Yes, that means your bladder is full and you probably need to go to the bathroom there. Major component of acid rain, yeah, it's going to be the rain portion, right? So obviously we can make things sound way worse than they actually are. And the truth is that a lot of compounds, as safe as they may seem, can be very dangerous. Even if, for example, we can breathe in oxygen. Oxygen is a compound that we need to breathe in all the time. But too much oxygen can also be very bad for us. I have one more quick story of why it's important to know chemical formulas and names. One day I was in the teacher's lounge eating lunch, and I noticed that there was a communal salt shaker on the teacher's lounge that had an interesting label that caught my eye. So I took a picture of it. Right from the start, it looks kind of like normal salt. It says iodized salt sense. It even says real salt down here. But what really caught my eye for this little container of salt is that it had 33% less sodium per teaspoon. Now, if you know anything about salt, you know that salt is made up of two elements, sodium and chlorine. It's basically sodium chloride, NaCl is the formula for salt. So normal salt in a salt container is 50% sodium and 50% chlorine. Now, this particular container is telling me that this has 33% less sodium, probably advertising it as some form of like a healthy alternative. But it really caught my eye because if salt is 50% sodium and 50% chlorine, and you're removing the sodium, what else is in this? So naturally, I took a look at it. I snapped a picture of it, and I looked at the back label and it said this: see, feel, taste the difference. The salt sense salt in 1 teaspoon had 1,560 milligrams of salt, okay, or sodium, whereas a regular table salt has 2,360 milligrams. So we're missing quite a bit of sodium for every teaspoon of salt. So that means they've had to add something else in here to kind of make it seem like we're eating salt, but we're actually not. So I took a look at the ingredients list. And if you don't know how ingredients list works, they always list all of the ingredients in order of how abundant they are, so how much they have. So the first ingredient in the salt, that's good news. It's salt, right? So that's really good that the main ingredient for the salt container is salt, because that's what it should be. But what really caught my eye is that all these other extra ingredients are added in here. The second one being silicon dioxide. If you don't know what silicon dioxide is, I knew this at the time. It's basically sand. All right, you can find it in dirt. You can find it in sand. That's basically what it is. It's a white powder that you could consume, I guess, in this sense, and it mimics the effect of the salts, like we're sprinkling it out. Then there's some other stuff here like tricalcium phosphate and potassium iodide. Those are two other versions of salt that kind of give it its taste. But some other things they've added: sodium bicarbonate, which is basically baking soda, and then dextrose, which is basically Splenda, like an artificial sweetener. So they've added all this extra stuff, which I necessarily wouldn't want to consume in my salt. All right, so it's really important to understand chemical names going forward. So we're going to talk a little bit more about that. But going into compounds, what exactly is a compound? Let's review this really quick. Well, a compound is going to be a combination of two or more atoms that are held together by some form of bond between them. So you can see here for the salt, you can see here Na and Cl, that kind of forms like this crystalline shape, this cube, where we have sodium and chlorine, and they have like pluses and minuses. So we'll talk about what that means later. Basically, for chemistry, there are three different types of bonds that can exist. They can be ionic, covalent, and metallic bonds. There are other type of bonds, things called like hydrogen bonds, but we're not going to get into that right now. The three main types of bonds that we cover are going to be the three main types of bonds that we're going to cover are going to be ionic, covalent, and metallic. Ionic being the important one for this section of notes. All right, what's really important to understand about compounds is that each compound has its own specific properties that may not always be like other similar compounds. For instance, carbon monoxide over here and carbon dioxide over here, they look very similar in the sense that they both have a carbon and they both contain oxygen. This one only contains one oxygen, whereas this one contains two oxygens. All right, they're both gases that we typically don't want to breathe in. And in fact, if you know a little bit about anatomy, we know that humans breathe out carbon dioxide. So this is what we breathe out after our lungs and our cells have processed the oxygen. So we breathe out carbon dioxide. Carbon monoxide is a byproduct of burning fossil fuels, and it's actually a very dangerous gas for us. It can cause a lot of neurological issues. It can even, in extreme cases, cause death if we're exposed to it for too long. The same thing is true for carbon dioxide, but carbon monoxide is way more dangerous for us than carbon dioxide. So even though they look similar, it's important to know that compounds can have different chemical properties, even if they're different by just one atom. So chemical formulas are used to show what combinations of atoms exist in a certain compound. So we see these chemical formulas all the time. The one that we're going to take a look at is an example of water. So we know what water's chemical formula is H2O. What does that mean? So we're going to have little indications here what each part of it means. First, we're going to have all of the symbols for each of the element. Remember, the elements begin always with an uppercase letter. So if you ever see a lowercase letter, that means that the letter is going to the element that has the uppercase. So right here, we only see an uppercase H and an uppercase O. H means that that's the symbol for hydrogen. O is a symbol for oxygen. Now we have to talk about how many we have here. So over here we have the subscript where we have a 2. This 2 indicates that we have 2 hydrogens. So the subscript always follows the element that we want to address. So the subscript 2 goes to the hydrogen. The oxygen has no subscript. So we don't need to write number 1 if there's only one of those elements. Right? So implied here that there's a subscript of 1 indicating 1 oxygen. So just a reminder, chemical formulas, we do not write the number 1 as a subscript. We only write numbers if we have more than 1. So here's another example. We have Al2O3. So let's try to identify what exactly we have here. Well, we have 2 aluminum atoms and 3 oxygen atoms. All right, so that's just our example. Let's go ahead and take a look at practice problem number 1 and see if we can practice a few of these compounds. So we're going to go ahead and work on practice problem number 1. If you want to work on these on your own, go ahead and pause the video right now, and then you can try to work on these 4 problems on your own. Otherwise, we're just going to keep going. So the first one right here, we have a CaNO3 and then a 2, and then the NO3 is in parentheses. So this one's kind of tricky because we haven't seen a format like this before. We have a lowercase letter a, again, that is indicating that it is going to the C. The letter C by itself, if you don't know, that is the element carbon, but this is going to be calcium. How many calciums do we have? Well, we only have 1 calcium because there's no subscript over here. So just 1 calcium. Okay, and then we have an NO3 in parentheses. Okay, so let's concentrate on that first. The NO3 right here, we have so far 1 nitrogen, and then we also have 3 oxygens. But what we can see here is that with this number 2 means that we have 2 of this entire group right here. So you could have probably guessed that we have actually 2 nitrogens, right? So I'm actually going to erase this. So overall, we have 2 nitrogens because we're multiplying that 2 out. You actually have to distribute that 2 out. So 2 nitrogens and then 6 total oxygens. So how many atoms are there total? There's a total of 9 atoms here. Okay, what about H2SO4? This 2 goes to the hydrogen, so there's 2 hydrogens. I'm just going to put the letter now. There's only 1 sulfur, and there are going to be 4 oxygens. Okay, so how many total elements are there? 2 plus 1 plus 4. That means there are 7 atoms total. Okay, what about CaOH2? Again, with these parentheses groups, those can be kind of tricky, but what you want to do is whatever number that you have on the outside, you want to make sure that you distribute it to everything that goes in the parentheses. So this 2 goes to the H, and this 2 also goes to the O. So we only have 1 calcium. We have 2 oxygens, and we have 2 hydrogens. So a total of 5 atoms. All right, once again, we're distributing this 2 out to everything. So this 2 goes to the H4 and the 2 goes to the N. So we only have 2 nitrogens because we had to multiply that 2 out. And then we have a total of 8 hydrogens. And then 1 selenium. Okay, so a total of 11 atoms. So just as a review of what this means, NH4 is something that looks like this. So we have a nitrogen in the middle with 4 hydrogens. And then there's something called a lone pair, which you don't really need to know right now. But it basically says that we have 2 of these. Okay, so we're going to have another one right here. And then I'm going to actually get rid of that lone pair. And then there's a selenium in the middle. Okay, so that's what the atom looks like. And basically what that 2 is telling us is that we want to make sure that this whole thing is grouped together. This NH4, that's one entire group stuck together. Okay, and so if we have 2 of those groups, we need to indicate that those 2 groups are together. The NH4, that's a key thing. This is kind of like one compound that's kind of important that it makes All right, so now that we have a good understanding of what compounds are and how to write chemical formulas, let's go ahead and start talking about ions. Well, what are exactly ions? Ions are formed when an atom either is going to gain or lose electrons. So remember last unit that we covered what isotopes are. Don't confuse an isotope with an ion. An isotope is an element that has a different number of neutrons, whereas an ion is going to be an element that has a different number of electrons. So up until this point, we have been learning that the number of protons and electrons for a specific atom is going to be the same, right? But sometimes we could have an instance where the number is going to be different. So let's take a look at fluorine really quick. Fluorine has 9 protons, so we can expect it to also have 9 electrons, right? But if it is going to gain or lose electrons, it will change. So what happens is we sometimes have a fluoride ion where the number of protons remains the same, because remember it's the same element, so the protons can't change, but the electrons did change. So now we went from 9 electrons in fluorine to 10 electrons in fluoride. Notice also the name change. We also went from fluorine to fluoride. We'll talk about that more in a little bit. But what we notice here is that the outer ring here, the valence electrons here, they have a pattern. So they are kind of put in pairs. So we have 2, 4, 6, and then you have this 1 by itself. So that's 7, right? Now, most elements want to have 8 electrons in their outermost orbital. So these ions want to have 8 valence electrons. So you can see here in the ionic form, we have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons once fluorine has gained an extra electron. So that's why it only gains 1 more electron. So if we have this fluoride ion, we want to consider that the number of electrons gained or lost is written as what's called the oxidation number or charge of the ion. So those two terms are synonymous, oxidation number or charge. So whenever I mention oxidation number or say the word charge, they're both the same thing. So the fluoride ion, what is its oxidation number? How do you find the oxidation number? Well, you do the protons minus the electrons, and that will give you the charge or the oxidation number. So we have 9 protons from fluorine, and now once it turned into an ion, the fluoride ion, it now has 10 electrons. So what is the charge now? Well, if we do protons minus electrons, 9 minus 10 is -1. Or the oxidation number, which is written in the top right, is going to be -1. So we have this F and then -1 in the top right. So taking a look at the periodic table, filling out those valence electrons might be a little bit tricky sometimes, and it could be kind of tedious just drawing out all the valence electrons or remembering the valence electrons. So we want to understand this a little bit better. Is there a pattern to the ions? Is there a way I could take a look at the periodic table and just quickly know what the charge of the element is going to be? And the answer to that is yes, there is a pattern. So this first column, so all of the alkali metals plus hydrogen, hydrogen, remember, is not a metal. The alkali metals plus hydrogen, they all going to form an ion with a +1 charge. The alkaline metals are going to form a +2 charge. We're going to skip the transition metals in the middle, skip that for now. Move on to the boron group, that's going to be +3. The carbon group, there is no pattern here because it could either be a +4 or a -4 sometimes. And then we have -3 for the nitrogen group, -2 for the oxygen group, -1 for the halogens, and then no compounds. You can say 0 here for the noble gases. So it's +1, +2, +3, no pattern, -3, -2, -1, 0. So that's the pattern for identifying what kind of charge these elements would have if they were to form an ion. Again, normally these elements like to have a charge of 0, but when they do form an ion, that's the charge they're going to be making. And let's take a look at one quick example. We have sodium and chlorine. That's the one we were talking about earlier with salt, sodium chloride. Notice that sodium has a +1 charge and chlorine has a -1 charge. It is no coincidence that those two numbers are the same but also opposite of each other. So +1 and -1. Those are going to match up well with each other because when these ions group together and form a compound, they will start to balance out the charges so that the charges equal out to 0. So let's take a look how this works really quick. If fluorine were to gain 1 electron, remember that electrons are negative. So if an electron is negative and you're gaining more negativity, then you're going to become a negative ion. What about sodium, for instance? Well, sodium loses an electron, so it becomes a positive. If it loses its negativity, it's going to become more positive. Right? So taking a look at this example, if the fluorine gained an electron, it went from 9 to 10. It's protons minus electrons. 9 minus 10 equals -1. So that being said, the sodium ion is going to have a charge of +1 because it has 10 electrons. Right? So I know we have a question mark here, but if we lost an electron, we would have 10 electrons here. So whenever we have a negative ion like this fluoride ion, that is called an anion. And a positive ion, that is going to be called a cation. All right, so let's take a look quickly at practice problem number 2 and see if we can fill out this whole chart with not only the ions, but also the number of protons, electrons, and the charge. All right, practice problem number 2. Once again, if you'd like to fill this out on your own, go ahead and do that now by pausing the video. Otherwise, we're just going to keep going forward and try to answer all of these blanks here. So the atomic numbers here have been filled out for the first 3, and then we have to find them later. So we can use a periodic table for that later. But what we want to do is identify the number of protons, electrons, and charge. Sodium has been already filled out for us, so let's move on to chlorine. The atomic number for chlorine is 17, so that was given to us from the periodic table. Now remember that we covered this in Unit 1. The number of protons is going to be equal to the same number as the atomic number, so that's going to be 17 as well. So protons and atomic number are always going to be the same, right? The charge can actually be indicated here from the chlorine. Notice for the charge of sodium we had a +1, and it has a plus in the upper right corner. Well, if we have a minus here in the upper right corner for chlorine, that means the charge is going to be -1. Now remember, charge is always going to be protons minus electrons. So protons minus electrons equals charge. I'm going to put that here in the corner so that we remember it. So that being said, what number do we put here for the electrons in order to get -1 charge? We get 18 electrons. We know that chlorine is going to have 18 electrons. All right. The next one, we don't know the ion, so let's go ahead and take a look at a periodic table and find the atomic number 8. Number 8 on the periodic table is going to be oxygen, right? So we can go ahead and put in the letter O for oxygen there. It has 8 protons because the atomic number is 8. And we are given that the number of electrons that it's going to have when it forms an ion is going to be 10. So 8 minus 10 is going to be -2. So now we actually have to go back here to the upper right corner of oxygen, and for the ion name we have to put in a small -2 in the upper right corner. All right, the next one we have potassium. So let's take a look at the periodic table, find out what number potassium is. It's right here. It's number 19. So the atomic number is 19. So the number of protons is going to be 19. And potassium has a +1 charge. I know this because if I take a look at the symbol right here, it has a plus sign right there. And there's no number next to it, so that just means 1. So +1. And so I want to find out what number protons minus electrons gives me +1. That number is going to be 18. All right, I have sulfur next. Sulfur is the next one on my list here. Sulfur is going to be right there, and its number is 16. So the atomic number is 16, which means the number of protons is also 16. Now we don't have charge, but we do have the number of electrons. 16 minus 18 is -2. We also could have just gotten that from looking at the upper right corner here of the sulfur. So that's actually what we can do for the next one. Magnesium, we have a +2 here. All right, and I don't even need to look at a periodic table because I know protons minus electrons gives me charge. So what -10 gives me 2? The answer is going to be 12. So the atomic number for magnesium is 12. And if you wanted to, you could always double check by taking a look at the periodic table, and magnesium is right here, number 12. So now that we have a good idea of what ions are and how they're basically just elements with a different number of electrons, what we can actually start to do is start to mix them together and form things called ionic compounds. Remember that some ions wanted to gain electrons and some ions wanted to lose electrons. So it just makes sense that they would pair up together and form these compounds. And they form compounds when the electrons are transferred from a positive to a negative ion, right? And they almost always include a metal and a non-metal. We might have recalled this from the intro to this unit that we covered earlier. A metal and a non-metal are always going to be part of an ionic compound in the chemical formula. So for instance, the example that we have here is going to be sodium and chloride. So we have this thing called the octet rule, and basically what the octet rule means is that most of these electrons, what they want to do is these elements want to have 8 valence electrons on the outer shells, right? So a sodium here has 1 valence electron normally, and chlorine has 7. Well, chlorine can easily get 1 more by taking it from someone else, but sodium can't gain 7 more. It's too difficult for the sodium to gain 7 electrons in order to fill this outer shell. Plus, if it were to do that, it would have a very negative charge, which it really doesn't want to have. So sodium has the option of just getting rid of this next electron on the very end, this valence electron, so that this shell right here ends up being its outer shell. And that one does have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So in this case, sodium meets the octet rule because its outer shell has 8 valence electrons. And chlorine, which has this extra electron donated from sodium, now has 8 valence electrons as well. So that's why they pair up very well, because sodium wants to lose 1 and chlorine wants to gain 1, so they're going to pair up. Sodium is the metal, chlorine is the non-metal in this example. Ionic compounds, some properties of them, they are going to exist mostly as crystalline solids. So if you've ever taken a look closely at salt, maybe, it does exist as a crystal. And a lot of these ionic compounds are going to form these crystalline shapes. They do conduct electricity when melted or when they are dissolved in water, and the reason for that is because there is a metal in the compound. So in the compound sodium chloride with salt, sodium is the metal and sodium does conduct electricity. So if you take salt and dissolve it in water, that water now has a metal dissolved in it, and so the water is now going to be able to conduct electricity as well. The other thing that we want to mention with ionic compounds is when we have the formula for the ionic compounds, we want to make sure that we contain the correct number of each ion to create a neutral compound between positive and negative ions. So that's very important. We want to take a look at the positive part and the negative part of these compounds and make sure they balance out to 0. For example, sodium, we know when it creates an ion, it has a +1 charge. And chlorine, when it forms an ion, has a -1 charge. And if you don't remember the chart from earlier, let's see if we can go back really quick. The chart from earlier showed us the, this is the chart right here. So this chart right here showed us the pattern. Sodium would always form a +1 charge based off of that pattern. And then chlorine, which is way over here, would always form a -1 charge. So we can see here that the +1 and the -1 are going to bond together to form a 0. +2, -2 will bond together, +3 and will -3. But there also could be other options here. So for instance, a +2 can bind with 2 -1s. So you could have, like, for instance, MgCl2. And in that case, the charges still balance out to 0. Right, so let's fast forward here just a bit. So the last thing we want to mention here for the ionic compounds is how they are named. The positive cation on the left side, the name is going to stay the same. The name of the element is going to be the same. For instance, we have potassium, and it creates a potassium ion. The nonmetal on the right side, the negative anion, that ending does change. It changes from INE typically to IDE. Okay, so instead of chlorine, it's going to be chloride, or sometimes we have to kind of make it up and add IDE at the end. So that's the end of the element. So if we mix potassium and chlorine together, we get what's called potassium chloride. So we change the ending of the last element to be IDE. So potassium chloride. Sodium and chlorine, for example, give us sodium chloride. Calcium and oxygen give us calcium oxide. Lithium and oxygen give us lithium oxide. So one more thing we want to mention is something called a Lewis structure or a dot diagram. And the best way for me to kind of explain how a dot diagram works is just by giving you an example. So we're going to take that same example we've been talking about all video, which is sodium chloride. And what we want to do is make a note that sodium has 1 valence electron, and we want to know that chlorine has 7 valence electrons. So we have to use our little trick of remembering what those valence electrons are. And I'll show that trick once more in the practice problem when we get to it. But we just want to make a note of the valence electrons. And what we're going to do for the Lewis structure or the dot diagram is write the symbol of the element followed by the number of valence electrons. And the number of valence electrons just basically surrounds the element. So we know that sodium has 1, so we're going to put 1 dot for that 1 valence electron. We're not doing the total number of electrons, just the valence ones. Chlorine, for instance, has 7 valence electrons like we mentioned before, so we're going to put 7 dots around it. And the dot diagram, what it's going to do is just show us the movement of the electrons from one atom to the other, and that's how they're going to create a bond and kind of bond together to form a compound. So this 1 electron from sodium made its way to the chlorine right here. So we're showing that sodium loses 1 electron and chlorine gains 1 electron, and then they're going to bond together, forming an ionic compound. So we have Na plus 1, Cl minus 1. So the final formula was NaCl. All right, so let's take a look at practice problems 3 through 5 and work on those right now. Once again, if you want to tackle these on by yourself, go ahead and pause the video now and you can work on these and then come back and check your answers. Otherwise, we're just going to work through them right now. So number 3 says, what is the formula for calcium chloride? So we want to take a look at calcium chloride and kind of figure out what that formula is going to be. The way I would solve these problems is I would first write out the elements that I'm dealing with. So I know I'm dealing with calcium, so that's Ca, and then chloride actually comes from the element chlorine. So I'm going to put Cl. So I'm going to write out the symbols for those two. The next step is going to be identify the charges for each of those elements. So for calcium, we know that calcium is in the second row, and if we do our little pattern here on the periodic table, we know that the charges are +1, +2, +3, no true pattern, -3, -2, -1, 0. And again, we're skipping this middle section. That would be the transition metals. Calcium is in the second row, so it's got a +2 charge. And then chlorine is in group 17, so that's going to be a -1 charge, so that's going to be right there. Okay, so if you wrote out CaCl as your answer, that technically would be incorrect. And the reason for that is because these charges don't balance out to 0. +2 and -1, they don't equal out to 0. So if you have a +2 on one side, you have to have a -2 on the other side. So the only way to do that is if we increase this side, the negative side, by 1 more -1. Right, so if we had 2 of these chlorines and each one have a -1 charge, they both add up to a -2. So if we had 2 of them, that's what we'd have to put there. CaCl2. All right, and what I'm actually going to do here is I'm going to just kind of recolor this so that we're being consistent. And I'm going to keep the positive ions blue so that the dot diagrams actually make a little bit more sense. So for the dot diagram, how would we draw that out? Well, we have Ca, which is calcium, and if we follow the rule of the valence electrons, we know that calcium has 2 valence electrons. So I'm going to actually go write out the rule for the valence electrons up here. So the first column was 1, and then 2, and then we skip the transition metals, just like we do with this charge pattern. Then it was 3, 4, 5, 6, 7, and then 8 valence electrons. So this was for valence electrons. So we actually have 2 patterns now. We have the valence electron pattern, and then we have the ionic charge pattern. So don't confuse those two because it can get very confusing very quickly. So for the dot diagram, we want to look at the valence electron pattern. And calcium, since it's in this column, it's going to have 2 valence electrons. 1 and 2. So we'll just draw them like that. Then we're going to put chlorine, and we have 2 of those. So we have a chlorine here, Cl, and then Cl. And chlorine, if we take a look at our valence electron pattern, has 7 valence electrons because chlorine's right there. So it's got 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the way you draw these dot diagrams is that you want to fill out these octet rules. So calcium wants to get rid of its +2 charge, or wants to get a +2 charge by getting rid of 2 electrons. So that's what it wants to do. And chlorine has a -1 charge. So each chlorine, because it has a -1 charge, is only going to gain 1 electron. Remember, electrons are negative, and the more you have, the more negative you have. So if chlorine is -1, it's going to donate, the calcium is going to donate that 1 electron right there. And this calcium is going to donate its other electron right there. So that's the dot diagram for calcium chloride. All right, so number 4 says, what is the formula for aluminum oxide? Just like I did with the last problem, what I'm going to do is first write out the elements that I have. So the positive one is always going to be first. So calcium is going to be the positive one here. Aluminum is going to be the positive one here. And for the next one, when we get to it, magnesium is going to be the positive one. The negative one is going to be chlorine in this first one, oxide in this one, and then oxide again for this one. Where does oxide come from? Well, oxide comes from the element oxygen. So I'm going to put that in red right there. The next step, what I wanted to do was identify the charges. So for the element aluminum, looking at my cheat chart right here, I'm going to use the pattern here on the bottom because that's going to be for the oxidation number, or for the charge. So aluminum is +3. Oxygen is going to be right there, which is right under -2. Okay, so we have a +3 and a -2. I'm going to give you guys a little tip here. The only way you're ever going to get a +3 and a -2 charge to equal out or to balance out each other is for them to both get to 6. So you either have a +6 on one side and a -6 on the other side. All right, so in order for that to happen, aluminum would need to add one more. So we have a +3 and a +3. So the total charge here is going to be +6. For oxygen, we have -2. Let's go ahead and add another one. That's -4. And then we're going to add another one. That's another one, -6. Okay, so we have +6 and then we have -6. So the final formula for this is going to be Al, so we have aluminum, and we have 2 of those, so we're going to put a little 2 there. We're going to put an O for oxygen, and then we have 3 of those. So the final formula is Al2O3. So that dot diagram is actually going to look a little bit tricky. So we have 2 aluminums. Let's go ahead and draw those out. And each aluminum had 3 valence electrons. So we're going to go 1, 2, 3, 1, 2, 3. Oxygen, there's 3 of those, so we're going to put 3 oxygens just like this. And each one has 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so oxygen, because it has a -2 charge as an ion, that means it's going to be gaining 2 electrons. Aluminum has a +3 charge as an ion, so it's going to be losing 3 electrons. So oxygen needs to gain 2, aluminum needs to lose 3. So let's go ahead and draw this dot diagram of how this works. So aluminum lost 1 electron here, went right there. Another one went right there. Then it has this third one. That third one can actually go to this middle oxygen. And it's kind of like the same thing on this side. So the aluminum loses one electron there, and then another electron there. And then this electron will come down over here. All right, number 5. This is going to be the last time we kind of review writing out a chemical formula, but we're going to do it the exact same way. So step 1, again, is just to identify the elements. So we have magnesium, and oxide comes from oxygen, so that's O. All right, step 2 is to identify the charges of those elements. So magnesium was in the second column right here, so if I'm taking a look at the charge pattern here, it's got a +2 charge. Oxygen has a -2 charge. Okay, then you have to identify, does the charge on the left and the right equal out to 0? In this case, it does. +2 and -2, they do balance out to 0. That means you only need one of each in order for it to be balanced out. So in this case, we have MgO. All right, so that's the final formula for that. I'm actually going to put a box around all of these so that we know what the answers are. Okay, and then for the dot diagram, we want to use the amount of valence electrons. So magnesium has 2 valence electrons, so I'm going to go ahead and draw those out. 1, 2. And oxygen has 6 valence electrons. So here's oxygen. 1, 2, 3, 4, 5, 6. And so magnesium has a +2 charge, so that means it's going to be losing 2 electrons. And oxygen has a -2 charge, so it's going to be gaining 2 electrons. Well, there's only one possible way for that to happen, and it's just like this. So magnesium lost its 2 electrons to oxygen that way. All right, so just as a recap, I've typed out some instructions on how to solve for a ionic compound formula every single time. I'm going to go ahead and hide here, and then you can actually see these instructions. I'll change the font color so it pops out a little bit more, so it's easier to read maybe. But basically, to make a chemical formula for these ionic compounds, the steps that we took were: 1, identify the elements that we had. 2, find out what those charges were, so we identified the charges. 3, balance out the charges by adding more of the same elements you already have. And then 4, write the formula based on how many of each element you have. So for instance, we had aluminum over here, and we had a +3 and oxygen -2. And I mentioned before, the only way for them to balance out is if they both get to 6. So we have +6 and -6 by adding 2 aluminums and then 3 oxygens. So that's how we did that, and then you write the final formula based on how many you had to add. An easier version of that was CaCl2, where we have calcium with a +2 and a chlorine with a -1, but we needed 2 chlorines to balance out the +2. That's why we have CaCl2. And then finally, for magnesium and oxygen, they were already balanced, so we only needed one of each, so it was just MgO. So those are the final steps for finding the chemical formula for ionic compounds.